Okay, let's do some examples. So let's look at some finding enantiomers, finding diastereomers, drawing enantiomers, drawing diastereomers, all that kind of stuff. And then we'll, because I think those kinds of examples, seeing how this works is sometimes the best way to learn this stuff because we've thrown a lot of terminology at you so far, but I really haven't given you an opportunity to practice this very much. So I'm going to throw some examples at you and we're going to see where this goes. Okay, so if I give you a structure, let's say a structure that looks like this, right? And we put bromine in the middle here, and hydrogen, right? So I'm going to ask you to find stereocenters. Okay. So there's one example. Let's do one that looks like this, right? Let's see, what else do we got? Wow. Pretend that those touch chlorine, chlorine, right? So in all these examples, can we find the stereocenters, right? And so let's go through our idea. Oh, here's a good one. This is a good one to try. Um, apparently into 5-membered rings today. Right? So let's go through these and see what kinds of things can we eliminate, right? We can eliminate any, right? So any sp3 carbons with more than one hydrogen, right? So it can't be this CH3, it can't be this CH2, it can't be this CH2, it can't be this CH3, right? CH2, 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 all those are out. CH3, CH2, CH2, CH3, right? So you can see pretty quickly, we can kind of identify where it's likely that these types of stereocenters are going to exist. They're not going to be at positions that are CH3s. They're not going to be at positions that are CH2s. And so hopefully, as you've been kind of practicing this finding of all the hydrogens that are part of these molecules, you've been kind of noticing what a CH2 group looks like, what a CH3 group looks like, etc. Right? So we can eliminate all of those, and that really leaves just these types of positions remaining, right? Where we have a single hydrogen or no hydrogens at all in some cases, right? As potential carbons that can be stereocenters, right? And so really quickly we can narrow this down. Here's the other thing, right? We can't have, so no sp3 carbons with more than one hydrogen, no sp2 or sp carbons, right? And so we can eliminate this carbon right here, right? Because this carbon has a pi bond attached to it, right? The carbonyl carbon is one that consistently students will choose as a stereocenter. It cannot be a stereocenter, right? If there's a pi bond to a carbon, there is no way for that to be a stereocenter, right? It can't be a chirality center. Okay? And now we're left with just, what do we have? 1, 2, 3, 4, 5 choices on these 4 molecules where stereocenters might exist, right? So now all of these are sp3 carbons, right? And then the second, so we can check that off. And then the second thing we have to check is, do they have 4 different groups attached? Right? And now thankfully we don't have to go through every carbon, we can just go through this one, the ones that are circled, right? So at this position we have a hydrogen, a bromine, those are different. We have a 2-carbon chain over here, and we have a 2-carbon chain over here. So this is CH2, CH3, this is CH2, CH3. These are the same group, or the same type of group, right? They're both 2-carbon chains, and so there is no stereocenter in this molecule, right? Same thing over here, right? Obviously we have a chlorine and another chlorine. These are the same group, and so there is no stereocenter in this molecule. The other 3 that we've circled are all stereocenters, right? This OH group, so we have an OH, We have a hydrogen that I haven't drawn in, but there's a hydrogen that's implied there, so that's group 2, right? We have a CH2 group as group 3, and then the rest of the ring as well. And then over here we have a CH that's got an OH attached to it, so that's different from the CH2, so we have group 3 and group 4. So this carbon has 4 different groups. It's an sp3 carbon. This is a chirality center or a stereocenter. Same thing down here, right? This is a compound that, or position has 4 distinct groups. Now, the 4 groups might be the same 4 groups that are attached to this other stereocenter, but that doesn't matter, right? It matters, are they different from each other when they're attached to this carbon? So again, we'll draw in the hydrogen just to prove that it's there. We have an OH, we have an H, we have a CH2, and we have a carbon here that has a hydrogen and an oxygen on it. And so this carbon is different from this carbon. So we have 4 different groups. So we have another stereocenter. All right, last one here. Is this a stereocenter? I think this is the most tricky of the bunch. This is not a stereocenter. It does not pass the 4 different groups test. Right? So we have a carboxylic acid as one group. We have a hydrogen, again, that hasn't been drawn in, but we can draw it in now. So we have a carboxylic acid, we have a hydrogen, those 2 groups are different. And then over here we have a CH2, and on the other side we have a CH2. So those are the same, and no matter how far we go out, we have another CH2, another CH2, no matter how far we go out, this compound is always going to have the same groups attached to it, right? And so it's not a stereocenter. It does not have 4 distinct groups. Okay. So that's finding stereocenters. Those are the kinds of tricks that you can play, right? So compounds that have symmetry, I hope is what you're seeing, right? So when we look at symmetry, right, this compound is nicely symmetrical. If we kind of draw a line right down the middle of this molecule, right, it's the same on both sides. If we draw a line right down the middle of this molecule, kind of splitting these 2 chlorines, there's a chlorine on each side, and this is the nice flat molecule down the middle. This molecule has some nice symmetry. If we cut it right here, right, you got 2 carbons on each side, it's symmetric, right? So symmetric molecules, because they have kind of the same groups attached to carbons, end up not having any stereocenters. Okay? And so there's 3 examples there of compounds that have wedges and dashes but don't have stereocenters, or they have positions that look like they might have 4 different groups, but turns out they don't. Those are the kinds of tricky things when you're looking at stereocenters. That's the kind of thing that may sometimes trip you up if you're not careful. So make sure that you're going through and counting up your groups, looking at the 4 groups that are attached to a position, and they have to all be different. Right? One last example, because they can be different a long ways away. Oops, I'm on the wrong, there we go. So let's look at this one. So we have, let's put a fluorine here and a chlorine here, right? And then I'm going to put a bromine way out here, and I'm going to put an alcohol way out here. Right? Is this a stereocenter? Whoops, pretend I pointed that arrow at the actual carbon. Is this a stereocenter? Right? It's got a fluorine, it's got a chlorine, and it's got a bunch of carbons attached to our sp3 carbon in the middle. Is this group different from this group? Right? If these 2 groups are different, then we have a stereocenter. If they're the same, then we don't. And even though the OH is very far away from the stereocenter and the bromine is very far away from the stereocenter, these are different enough. So this one is a stereocenter. 4 different groups attached to sp3. So even though the groups seem to be the same for most of the molecule, even though that's whatever 6 carbons removed from the stereocenter, that's still different enough to make it into a stereocenter. So I hope that's kind of helpful in identifying stereocenters and kind of looking at wedges and dashes and getting used to looking at that kind of stuff. We're going to do a couple of exceptions to uh, the stereocenter rules that we've already talked about, and that should wrap it up for this week. All right, so see you in the next one.